Okay, this is chapter 6, quiz. Which of these phenomena suggests that light acts as a particle? Okay, well, not this one. This one is a wave. And remember, Thomas Young said this. Reflection, that is a particle, and it was Newton that described it as a particle because of this. Not refraction, that's as a wave. And remember, that was Huygens. And the photoelectric effect, that is a particle. And remember, that was Einstein. So I have the photoelectric effect and reflection, both of which show that it's particle. That's 2 and 4, so C is the right answer. Figure shows an incoming ray. It says that this angle is 30 degrees. What is theta 2? Well, if that's 30 degrees, that's 30 degrees. Then that has to be 60 degrees because that's a right angle. And so that has to be 30. That has to be 60. And then by the law of reflection, this has to be 60 degrees. Remember, it's not drawn to scale. It's not as it's drawn. As it drawn, this looks like it's 45, and this is 45. But that's not the case. The answer is 60. Light travels through 10-meter length of glass, index fraction of 1.5. How long does it take light to travel? Well, first we want to find the speed of light in the glass. That's V equals C over N, 3 times 10 to the 8th over 1.5. That's 2 times 10 to the 8th meters per second. So it travels slower in the glass. And then V is equal to D over T. Here I'm looking for T. 10 meters over 2 times 10 to the 8th. That's 5 times 10 to the minus 8 seconds. A. All right, this figure shows a light path that travels through 3 different materials, which describes the relationship between the indices of refraction. All right, so here I take my wave fronts. Here, notice that it bends away from the normal. That means that it speeds up. That means that N2 has to be less than N1. So if N2 is less than N1, that gets rid of this one and that one, both of which say that N2 is bigger than N1. Now I go here. It travels faster, or excuse me, travels more slowly in N3. That means that N3 is bigger than N2. See, because it slows down here and this comes around. So N3 is bigger than N2. Okay, well that gets rid of C. So A must be the right answer. But also notice that I could determine what is the relationship between N1 and N3. We'll see this come up on the concept test. By imagining I have the ray in N1 as it's drawn, and then the ray in N3 as it's drawn. Just basically getting rid of N2 altogether. My light rays come in here. They slow down when they enter N3, so I know that N3 has to be bigger than N1, which is what we have here. N3 is bigger than N1. And I realize these inequalities are not written correctly, but you would see them written correctly on the exam. We'll see another question like that in a bit. All right, here I have theta 1 is equal to 30 degrees. Oops, sorry. Theta 1 equals 30 degrees. I want to know theta 3. This is by the law of refraction. N1 sine theta 1 has to equal N2 sine theta 2. And N2 sine theta 2 has to equal N3 sine theta 3. So notice that these two are also equal, so that the relationship between N1 and N3, regardless of N2 and what it is between them, is still going to hold by the law of refraction, which is what we saw previously, where we could just remove that N2 and the angles would still hold. So here I have N1, which is pause for just a second. Okay, sorry about that. All right, so N1 is 1.2 times the sine of theta 1, which is 30 degrees. And then that's going to equal N3, which is 1.1 times the sine of theta. So here 1.2 times sine of 30, that's 0.6 divided by 1.1 equals sine of theta 3. And so theta 3 is the inverse sine of 0.6 over 1.1. And I get 33 degrees. Right, so 33 degrees is theta 3. And notice also that we see here that theta 3 is bigger than theta 1 as it's drawn, and as it should be, since the index n3 is less than the index n2, it should move away from the normal. Okay, this figure shows a person looking at a star in a box. Where does the person see the image of the star? Okay, so I have a light ray that comes up, and because of the way the mediums, that is that I have a high index here and a low index here, the light ray is going to bend away from the normal and go to this very dour looking person. And that will cause the star to appear, if I trace that ray back here. So the image of the star will be to the right of the actual star. Figure light travels from water to glass. What must theta 1 be for total internal reflection to occur? Remember, theta 1, total internal reflection occurs when theta 2 is equal to 90 degrees. So it's just a special case of the law of refraction. And so I would say, let's see, N1 sine theta 1 equals N2 sine of 90. And solving now for theta 1. So I have 1.3 equals 1.5. And then I solve that for theta 1. Okay, and if you actually try to put this in, let's see, this is 1.5 times 1. If I try doing the inverse sign of 1.5 over 1.3, I'll get an error, and so that this does not exist. And so let's go back and think about this. If I have my ray coming along in this direction, it's going from a low index to a high index. And so if I draw my ray, it's actually moving from a low index to a high index. It's going to be traveling faster here, so it's going to bend in this direction. My new ray will bend not away from the normal, but towards the normal. So I will not get total internal reflection that will occur because I'm moving from a low index to a high index of refraction. In order for total internal reflection to occur, you have to bend away from the normal so that your ray will travel along this point. All right, these are types of electromagnetic spectrum, ranging more from lowest to highest energy. Okay, well, the lowest of this lot is radio waves, microwaves, or next, ultraviolet, and then gamma rays. So let's see, radio, microwave, ultraviolet, and gamma rays. So A is the right answer. Which physical property of glass allows the creation of light dispersing prisms? That's going to be that the dependence of the index of refraction on wavelength. So if I were to plot the index versus wavelength, it looks something like this. All right. Which of the media is this light traveling faster? Okay, well, the one that's traveling faster is going to be the one, either medium 1 or medium 2, is the one that's going to bend the least. See, because it's traveling a certain speed in air, and then it's slower right here, so it bends in this direction. All right, so the one that's traveling faster is going to be medium 1. That's the one in which it bends the least. Whereas over here, it slows down a lot more, and so it bends more in this direction. Okay, parallel light rays cross from medium 1 and medium 2 and medium 3. What can we see about the relative size of the indices of refraction? Okay, well here it bends towards the normal, so I can say then that N2 is bigger than N1 because it slows down here and bends in this direction. So let's see, N2 is bigger than N1. Okay, that gets rid of D. All right, and then moving from N2 to N3, it travels faster in N3, so I can say that N3 is less than N2. All right, that gets rid of D, which we already have. N3 is less than N2. C is still okay. That gets rid of B. So now we have either A or C. So now we can think about N1 versus N3. So I have light rays that travel along here. Imagine N2 just isn't there. Actually, let me redraw this so you can see. That's going to be N1. This is N3. I have a light ray that comes in like this, and then it bends away from the normal. This is N1. This is N3. So my light rays travel in this direction, and then they speed up when they enter N3. So that tells me that N3 is less than N1 because light is traveling faster in N3. So N3 is less than N1. That gets rid of C. So A must be the right answer, and it carries all three of these inequalities. Shoot a fish with a gun, you should aim directly, slightly above, or slightly below. All right, well, this is like the star problem that we had. Imagine that I have a light ray that comes out. It bends away from the normal like this and goes to the person's eye. And so the light ray will look like it's coming from a fish that is right there, or you can imagine it to be right there, which would mean you would have to aim slightly below the fish, where you see the fish to be, and then you would actually hit the fish. However, if you're using a laser gun, then the laser gun will also refract just as the light ray from the fish. So the light ray from the fish comes out like this and goes straight to your eye. However, the laser gun will also refract and hit the fish, if you've ever been laser gun fishing before. All right, imagine you're an alien from another planet with infrared eyes. What do you see when you look around the room? Bright spots where the bodies are and dark elsewhere. All right, that's what you'll see. Bodies, human bodies, give off most of their energy actually in the form of radiation, but not in the form of visible radiation, but the form of light or infrared radiation. Since Superman is from the planet Krypton, his eyes are sensitive to the entire electromagnetic spectrum. Does this mean that he can use X-ray vision to see that Lois Lane is being kidnapped in the other room? No, he can't. Because if you imagine that Superman is over here and Lois Lane is in here, you know, Superman can see X-rays that are coming towards him. All right. However, Lois Lane does not give off X-rays, and so there are no X-rays for him to see. When you have an X-ray machine where you can see through these solid walls or solid materials, you know, you have a person laying on a thing. There is a source of X-rays that goes through the person, and then there's a detector on the other side. So it's like Superman is just the detector, but he doesn't have a source of X-rays. Actually, what we think that Superman actually does, I mean, Superman's not real, obviously, but he uses some sort of sonar or maybe even a ground-penetrating radar type system where he emits these low-energy waves, and then they bounce off, and then they come back to him, kind of like a dolphin does. And that's the end.